Okay, so if you're watching at home, please think about those 3 questions. All right, today, you guys, we're going to continue with quantum mechanics, and we're going to specifically get into the Bohr model of the atom. We've talked a little bit about the Bohr model of the atom, but now I want to get into the specifics of the quantum mechanical explanation of this model of the atom that we've been talking about. Here are the things that IB would like you to know about it. Outline laboratory procedure, explain how spectra provide evidence for quantization, calculate wavelengths of spectral lines, and explain the origin of the atomic energy levels. Okay, we have talked about some of this before. Yes, Daniel. Question? Okay. Okay. So, you guys, spectral lines have been observed for a long time. Well, not a long time, a couple hundred years. People have been observing these atomic spectral lines, and there had not really been a good explanation for it. But remember, where's the picture? There's the picture I'm looking for. Okay. This is a map of, I think, the spectral lines of hydrogen. And when people started looking at these, I think the first ones to be discovered were the Balmer series, because those are actually in the visible wavelengths of light. These are the ones that are actually visible light. Once you get out to the Paschken series, you're into infrared. Over here at the Lyman series, I believe these spectral lines occur in the ultraviolet region of the electromagnetic spectrum. So the Balmer series were the first ones to be observed. And once they started mapping them out, they noticed there was a pattern. I mean, if you look at it, you see there's a pattern. These guys, Balmer and Rydberg, whom those series, that one series is named after, discovered a mathematical relationship. They were able to give a mathematical equation that would allow you to calculate where these spectral lines exist. And here it is, the equation. 1 over the wavelength of the spectral line equals r, this constant, times really 1 over 4, but it just looks better if you write 1 over 2 squared, because you see there's this relationship, this inverse relationship between the numbers squared. And then the number n in the second part, n being an integer. It can be 1, 2, 3, 4, but it can't be anything in between. It can't be 1.2. It can't be 6.4. It has to be a whole number. Again, there wasn't a theoretical explanation for why this worked. It was just a mathematical description. But notice that there is quantization happening in this equation. Okay, to find these spectral lines, you have to have a specific integer in that equation, and you can't be anywhere in between. So it gives you an explanation of that. So moving along, then, we get to Niels Bohr. Now, Niels Bohr, we've talked about the Bohr model of the atom a little bit, and the Rutherford model, which had the nucleus, you guys stop talking, the Rutherford model, which had the nucleus of the atom at the center, and the electrons orbiting like little planets around the sun, was good. But Bohr said, you know what, we should be able to incorporate this new idea of the quantum nature of energy that Planck has introduced and Einstein has discussed. We should incorporate these theories into the atom. We should be able to also explain atomic spectra. So Niels Bohr set out to do that. And that is where the Bohr model of the atom comes in, which is an extension of the Rutherford model. So one of the things that Bohr said, he had some postulates that he came up with. And the first thing that he decided is that the angular momentum of the electrons should be quantized. If energy is quantized in photons, then the angular momentum should be quantized in the electrons. And he came up with an equation for it. Angular momentum is a lot like momentum. What is the equation for momentum? P equals mv. Excellent. And so that's just something moving in a straight line. But if something is rotating or spinning, it has angular momentum, and you have to incorporate the radius as well. So here's what we get for that. Okay. This is angular momentum. Mass times velocity times r. Okay. And he said that the electrons will have angular momentum equal to some integer, depending on where they want to be existing. Okay, some integer. This is the quantum condition, times Planck's constant divided by 2 pi. That number, Planck's constant divided by 2 pi, comes up quite a lot. This is actually a very common number in quantum mechanics and in relativity. It's so common that sometimes it's just written as h bar. Okay, so if you see h bar, that means h divided by 2 pi. All right. Hang on a sec. Oh, there we go. That's all. Okay, his second quantum condition. Bohr's second quantum condition says that electrons can only exist at these specific orbitals. They will make quantum leaps from one orbital to the next, and in doing so, they will either absorb a photon that has exactly that energy, or they will release a photon that has exactly that energy, and that is why we see spectral lines. Okay? That is why they see spectral lines, and this is the first explanation we had to why gases give off very specific spectral lines, because the electron's jumping up and down between their orbitals, and it basically allows us to suddenly calculate the radius of those orbitals and do some math in that situation. Now, Bohr, some of his things that he came up with, he did it very simply, you guys. He actually thought if the electrons are moving in little circular orbitals, they're going to have centripetal force. They're going to have centripetal force. And the centripetal force is going to be exerted by the electromagnetic attraction between the proton and the electron, right? So he could set that equal to KQQ over R squared, right? Remember that? Energy equals KQQ over R squared. This is how he actually started his thought process and worked through these equations, okay? And he then was able to find out the energy associated with each orbital, okay? The energy associated with each orbital. He used this constant K and N squared, and basically doing that equation of centripetal force, comparing it to the electromagnetic attraction, he was able to calculate this for hydrogen, and he found that the basic energy level for hydrogen, where N equals 1, that basic bottom orbital where N equals 1, has an energy of negative 13.6 electron volts. That's N equals 1. And then you can now calculate the energy level of N equals 2 and so on. And the reason it's negative is because just by convention, what they've decided to do when we talk about energy, you need to have a reference point. And remember, with potential energy, we talked about the reference point being infinity. And at infinity, you have 0 potential energy. And so when these electrons leave, okay, then they have 0 energy up here at N equals infinity. Okay? So what he showed was that, again, the energy of an atom is now quantized, and the way it's quantized is by where those electrons live, which orbital they go in. This energy right here, this is the energy of the first state. So basically, if I hit a hydrogen atom with a photon that has 13.6 electron volts, what would you expect to happen? If I hit a hydrogen atom with a photon that has a frequency such that its energy is 13.6 electron volts, what would happen? It would ionize the gas. That electron would absorb that photon with enough energy to be knocked off and gone away forever. If I hit that hydrogen atom with a photon that has less energy than that, what's the electron going to do? It's going to jump up. But it can only be if that photon has exactly the right amount of energy. If it doesn't have the right amount of energy, the photon passes right through and nothing happens. Okay?
Okay.
Okay?
So,
Yeah.
basically, if the energies don't match up.
Okay. So, with that, I don't know. Come on. There we go. Okay. So this idea of photons either being absorbed or emitted by atoms now was explained by Bohr. And basically, photons are given off when the electrons drop from one orbital to the next, or they're absorbed when they jump from a lower orbital to a higher orbital. The frequency of the photon can be calculated if we know the difference in energy between those orbitals. If we know the difference in energy, then just that difference in energy equals HF, and that's either the photon that's absorbed, the frequency of the photon absorbed, or the frequency of the photon emitted, okay? And this explains spectral lines. This explains why we don't have continuous spectra, why we have very specific spectral lines associated with each atom, because you have very specific energy levels for each orbital, and photons will only be absorbed or emitted when the electrons jump between those specific orbitals. There's an equation that kind of helps you figure that out too. Remember that the energy of an orbital is 1 over n squared. 1 over n squared, K being 13.6 for hydrogen. So now If I just find the different energy levels of the two orbitals, I find the difference between those, I multiply it by k, that tells me how much energy there is between those two orbitals, and that will tell me, then I can use that to find the frequency of the photon that gets absorbed or emitted. Now, get to see these again. There we go. Okay, so there's our equation. So let's just summarize the Bohr model here. The reason the Bohr model was good was because it made predictions that were correct. It complied with what was observed. At this point, I think when Bohr came up with this model, they only knew the spectral lines for hydrogen in the visible wavelengths. They didn't know about spectral lines in infrared and ultraviolet. When Bohr came up with this model, he calculated where these additional spectral lines should exist. People then went out and found them. That's a very good model. A model that makes a prediction that can be verified is usually going to give you an idea that you're on the right track. And that's exactly what he did. But there were some assumptions. Okay? Maxwell's theory of electromagnetic radiation, which had come up previous to this, Maxwell explained what electromagnetic waves are and that they get created by accelerating charged particles, specifically usually electrons. Well, in the Bohr model, you have electrons that are accelerating centripetally, and yet they're not giving off radiation. And why? Don't know. And Bohr didn't know. He just said they're not. Okay? When they're in their orbitals, they don't give off radiation. He said angular momentum was quantized. Why? Just seems like it should be. Okay? Didn't have a good explanation as to why. And he didn't have any way to explain how the electrons jump from one orbital to the next. He just said that they did, and when they do, it's kind of like they make this quantum leap. They cease to exist anywhere in between, but then they exist at this new level. Didn't know why. So it wasn't a perfect model, but the fact that it made predictions, and those predictions were correct, let us know that it was actually a pretty good model, good enough to give this guy the Nobel Prize in 1922. He was only 37 years old. Whew. Okay. Is that the youngest? I don't know. I don't know what the youngest is. Okay. Let's look at a picture here. See if we can connect all this. This bottom picture, spectral lines for hydrogen. So you guys, another limitation for the Bohr model, just so you know, and to me this is a pretty big limitation. I'll talk about it in a second. Okay. Here's the spectral lines on the bottom. This top picture is a picture to represent the energy levels of hydrogen. Notice the ground state has an energy of negative 13.6 electron volts. If we did the math with the equations I just told you, you could find that the energy level for n equals 2, the second orbital, would be negative 3.4. Okay? And then the third energy orbital has an energy of negative 1.5, negative 0.85, and so on. Notice, again, Jonathan, like we were talking about earlier, the orbitals get closer together as you go up, okay? And ultimately, they begin to overlap. What exactly would be the energy jump from orbital 2 to orbital 1? What would be the energy difference? Okay, 10.2 electron volts. And that's going to equal HF, which will allow us to calculate the frequency and therefore the wavelength of the photon that will be absorbed or emitted when an electron jumps between these two orbitals. You with me? What do we have to be careful of with what I wrote on the board? Excellent. This energy is in electron volts. If you use 6.63 times 10 to the negative 34th for H, you need the energy to be in joules. There's a different value of that constant for electron volts. It's out there. I don't know what it is off the top of my head, but there is Planck's constant with electron volts. Okay. Let's look at the relationship here. Okay. The Balmer series, which is the one that is visible light, the one that you've actually observed in this classroom with those glasses, is when these electrons were jumping down to n equals 2. Those energies correspond to visible light. Whenever they drop down to n equals 1, is this higher or lower energy? More or less energy? More energy. So is that a higher or lower frequency? Higher frequency. Is that a larger or smaller wavelength? Smaller wavelength. Is that infrared or ultraviolet? Excellent. So these are, I was a lot fast, okay? But anything dropping down to 1 is the Lyman series, which is going to be in the ultraviolet region of the spectrum. Anything dropping down to n equals 3 is in the Paschen series, which is going to be more infrared, okay? But this Balmer is visible. Now, give me, let's see, what I want you guys now to just theoretically think about. This spectral line right here. Please tell me now with what you know. You don't even have to do any math. You can look at the picture and figure this out. What energy level, which arrow is it on our drawing here? Is it A, B, C, D, or E? A. Okay. Which spectral line is it? Which orbital is it that gives us that spectral line? Some of you say A, some of you say, hopefully none of you are saying B, C, or D. Okay, hopefully you know it's either A or E. Okay, that's good. Is this spectral line, because it's got a bigger wavelength, so it has less energy, right?
Smaller jump.
Which means it's a smaller jump. Okay? And notice also that as we move up to these lines here, the difference gets less and less and less, right? The difference gets less and less and less, right? It's another way of looking at it. Okay. So there were definitely some issues with the Bohr model. The Bohr model was really good, and I've already told you why it was really good. But it works really well for hydrogen. It doesn't work for helium or anything else. No, because it did explain a lot to us, okay? But again, you get to more complicated atoms, it doesn't work. And to me, that's a pretty significant issue, but it works great for hydrogen. But who am I to argue? Who am I to argue? Okay. It didn't tell us why some lines were brighter than others, okay? It doesn't explain why atoms like to make bonds. And there were absolutely no experimental evidence as to why his postulates were true, okay? So yes, it's not perfect, but it was better than anyone had come up with before that time, because it actually did explain spectral lines of hydrogen, and it made predictions, and those predictions were correct. So there was something correct about it, but no, it was not perfect. Yeah, that's all we need to know right now. Okay. Okay, let's go back to Monsieur Louis de Broglie. Monsieur de Broglie. What did he say again?
All matter has wavelength.
Okay, all matter has wavelength. Anything that is like particles have wave nature, and the wavelength of a particle is equal to h over p, okay, or h over mv. Yes, it was proven by shooting electrons. In order to do it, well, in order to prove that something has wave nature, we tend to look for diffraction. Usually, that's the main way. If you can show something diffracts, then it's got to be a wave. And usually diffraction interference. And what they did was they shot electrons at, remember with diffraction, in order to get a wave to diffract, you have to pass it through an opening that is about the same size as the wavelength of the wave. Okay? What's that? Comparable to, exactly. So, and remember his thing, the wavelengths are really small. So we had to take electrons and shoot them at really small openings. Well, one of the people that came up with this, and I forget their name, I think it might have been Davison and Garner, they said, well, is that what it was? A really small opening would be like the opening between atoms. That's a pretty small opening. So they shot electrons at a crystal, which has a very specific atomic structure and has little small openings between the atoms, and they observed a diffraction pattern when the electrons went through the crystals. Exactly predicted by what de Broglie predicted. So yeah, experimentally it has been shown to be true. Now, if we could shoot you guys through a really tiny opening, we might see your wave nature, but that'd be hard to do, right? I mean, because remember, your wavelength is like super small, 10 to the negative, what? It was like way down there, super small. Okay, but let's think about this for a second. So he says that particles have wave properties. Awesome. And remember that Niels Bohr, his postulate is that angular momentum is quantized. Well, let's rearrange this equation. Let's rearrange Bohr's equation, okay, to say that 2 pi r equals n times lambda. Let's see if we can do that. I think we can do that. Should be able to do that, okay? This is cool. Okay, so by combining these two equations, we get that the circumference of a circle is equal to some integer times the wavelength of the electrons. Now, think about that for a second. The circumference of the circle, again, we have a quantum condition here that deals with the wavelength of the electrons, but it's giving us the circumference of a circle. And we're thinking about these orbitals in circular manner. So basically, when we combine Bohr's postulate with the de Broglie hypothesis, the orbitals that we get are the orbitals that are created where the wave nature of the electron would perfectly fit. The orbital is equal to some whole number multiple of the wavelength of the electron, so that the wave nature of the electron would positively interfere with itself, creating a standing wave, just like in a musical instrument, and that is why the electron exists there. Because it exists at the orbitals where it constructively interferes with itself in its wave nature and creates a standing wave. It can't exist anywhere else because its wave nature destructively interferes and cancels itself out. So the reason it exists at the orbitals is because that is where its wave nature allows it to exist. Okay? Totally crazy, but it explains because any other size orbital. That's why the photon takes away or absorbs the energy, okay? And that's why only very specific photons will interact with the electrons, because the electrons can only exist in their specific orbitals. This is what Bohr told us. He told us they could only exist at certain orbitals, but he didn't know why. But when de Broglie comes along and says, well, maybe electrons have wave nature, and you look at the wave nature with the Bohr idea, then it explains why the electrons only exist at specific orbitals. They'll only exist in the orbitals where their wave nature will constructively interfere with themselves and allow them to be. Okay? Here's kind of a picture of it. Okay? Here is the n equals 2 orbital. Now, this circumference is just the right length where it's 2 times the wavelength of the electrons. So they fit perfectly. And they can oscillate perfectly with themselves and constructively interfere with themselves and exist. At n equals 3, the circumference is such that you get 3 complete wavelengths perfectly. And 5. Anything in between, the wavelength doesn't match up, and it's destructive interference, and it cancels itself out. Isn't that crazy? I think it's crazy stuff. Okay? It is cool. I prefer to think about this more as kind of the circular orbits and constructive interference. IB, for some reason, likes to think of it as the electron in a box. And this is on the syllabus. This is one of the things they want you to think about. So an electron the way the electron in a box model works is the same idea, just in a straight line. That if I have a box with a certain length, the electron wave, I mean, it's just like our musical instruments. Exactly, same as the pipe thing, okay? The electrons will only exist when the length of the box is such that it has constructive interference. I just kind of put it into circular motion because I think that works better.
Would it work if it was the same as 1.5 times wavelength or 1?
No, in this case, it's got to fit whole number lengths of the wavelengths. And I can't remember if that was closed or open pipe. It was, yeah, okay. So it's kind of like that. No. So this is an equation that's in your data booklet. It's got lots of variables, okay? Basically, it allows you to calculate the energy that an electron has depending on its orbital, Planck's constant, the number 8, the mass of the electron, and the length of the box, or the circumference of the orbital. No, in this case, it's actually length. Okay? I know. I know. That's why we use them over and over, because we do run. Last thing to think about, don't worry, I'll come back to this, is, so we've got this idea that electrons are waves now, and their wave nature is the thing that allows them to exist at these specific orbitals. Great. And in the past, we talked about mechanical waves, and in order for a mechanical wave to happen, it needs some sort of a medium to pass through. And even an electromagnetic wave. What is oscillating in an electromagnetic wave?
Magnetic field
An electric field. Great. It's an oscillation between fields, electric and magnetic fields. So there's always something that's waving. But now we're talking about electrons as waves. Before we thought about them as little particles. So the $4,000 trillion question is, if an electron is a wave, what is it that is oscillating? What is it that is actually waving? Okay, because waves always have some sort of oscillation happening, and that's what we're going to talk about next time. Okay? Oh, I know.